This video is an introduction to organic chemistry. Organic chemistry is the study of carbon compounds. So anything containing carbon is considered organic. It used to be that they used to think organic was anything that was living, and all living things do contain carbon. Well, I shouldn't say all, most. However, the definition has increased to include more things. So anything that has carbon is what we consider organic. You have to remember the shapes of organic molecules and how to draw molecules, because the shapes are really important to determining their physical and chemical properties. So first in this unit, we're going to overview kind of how to draw them and how to name them, looking at their structures. And then that's going to lead into the second part, which is going to be about the reactions. So carbon has the ability to make single bonds, which are made of 2 electrons. It can make double bonds, which is 4 electrons. And it can make triple bonds, which are 6 electrons. And so remember, carbon as a nonmetal is going to make all these single, double, and triple bonds. These will all be covalent bonds, which, if you remember, means that they have shared electrons. So when I say 2 electrons in that single bond, that's 1 from each atom, and then they're sharing them. Double would be 2 from each atom for a total of 4. Triple would be 3 from each atom with a total of 6. So shapes that carbon can form are tetrahedral, trigonal, planar, and linear. So tetrahedral is going to be when you have carbon like this, like methane, for example, that has 4 single bonds. And these 4 bonds, so they're made of 1 s orbital and 3 p orbitals. So when they hybridize, meaning they're all going to be the same, they're going to be a hybrid. It's not 1 s and 3 p actually. They hybridize so that they're all equal. So each individual one is a hybrid, and we call each of those a hybrid of an sp3 because it's 3 p orbitals and 1 s. So sp3 hybridization in when you have 4 single bonds. Trigonal planar will be when you have something like carbon with a double bond to something like oxygen, for example, and then 2 single bonds. So 1 double, 2 single bonds. And what we get here, because we have electrons in 3 locations, we're going to have a hybrid of 3 orbitals. So it'd be 1 s and 2 p's. So that's sp2 hybridization when you have a trigonal planar shape. Linear can be made 2 different ways. It can either be 2 double bonds, which would look like carbon dioxide, C double bond O. Oops, come back here. Oh, hold on a second. Okay. With your 2 double bonds, it'll space out as far apart as possible and be linear. Or it can be 1 triple and, oops, I should have done and up here. 1 triple and 1 single. That could be like hydrocyanic acid. So that would be a carbon, triple bond to a nitrogen, and then single bond to a hydrogen. So that would also be linear. Because you have electrons in 2 sites, you're going to have a hybrid of 1 s and 1 p. So this is going to be an sp hybridization. So the properties of these organic molecules vary greatly. There's a huge range of properties that we're going to get into more when we understand their structures more. A lot of them, besides having these shapes and having single, double, and triple bonds, will also have what we call functional groups. Functional groups are going to be kind of like attachments, like little pieces that will attach to like a chain of carbon. So just hydrogen and carbon don't really have like a functional group, but if you add like a hydroxide, for example, that would be adding a functional group. So we're going to go into that whole list, but what functional groups will do is they will change the reactivity. They can change the solubility. And they can change acid-base properties. All right, so let's talk more about hydrocarbons. So hydrocarbons are anything that contains hydrogen and carbon, right? Hence the name hydrocarbon. There are 4 types of hydrocarbons, and we're going to go through these more in detail later and how to name them and how to draw them, but for now you should just be able to identify them. The first one is an alkane. And an alkane is when you have a hydrocarbon with only single bonds. When you have something like, let's do C2H6, like this would be an alkane. It only has single bonds. And we call these molecules saturated, meaning they have all of their bonds that they can have. Carbon cannot bond more than 4 times, so if it makes all single bonds, it's saturated, it's full. So the next group of hydrocarbons is an alkene. 1 letter difference, okay? And this is due to having at least 1 carbon-carbon double bond. All right, and when you have a double bond, it's not saturated anymore. So we call this unsaturated. It's not full because if you broke apart one of the pieces of the double bond, it could bond to more things. So an alkene would be like if I had a carbon-carbon double bond like this, so C2H4. This would be an example of an alkene. Okay, so the next one would be what we call an alkyne. So now we're just replacing the A or the E with a Y. And this is a molecule that contains at least 1 carbon-carbon triple bond. And this would also be unsaturated because, again, you could break up the triple bond and bond with more things. So this could be something like carbon, like this, C2H2. Carbon-carbon triple bond, it would bond to 2 H's. And you can see how these change the shape. All right, so the last one is what we call an arene, or you'll also hear them called aromatics. And you should know both words. These are hydrocarbons that contain a planar, meaning flat, ring structure. In other words, we call this, it has to have a phenyl group. Okay, and this phenyl group is this flat ring of carbons, 6 carbons, with alternating double bonds, like this. This is a phenyl group. All right, so anything with this is an arene or an aromatic. All right, so the last piece in the intro is what's a homologous series. So homologous series are groups of hydrocarbons that have the same functional group. Oops. So that could be like they're all alkanes, for example. They're all hydrocarbons with single bonds. Or they all have a hydroxide group, functional group on them. They have the same general formula. So, for example, CnH2n plus 2 is the general formula for all alkanes. You can go to like alkenes, which would have a general formula of CnH2n, right, etc. They don't have the same necessarily, but they have similar chemical properties. I mean, that's what makes them a homologous series, right? That homo means same. So similar chemical properties. So here's an example of a homologous series. CH4, C2H6, C3H8. These are all alkanes. They all have the general formula of CnH2n plus 2. And as you continue through the series, so you go from CH4 to C2H6 in that direction, molar mass increases, right? You're gaining carbons and hydrogens. When you have an increased molar mass, your London dispersion forces increase. If you remember, London dispersion forces are the forces that hold the molecules together. When you have a nonpolar molecule, these are the weakest. Okay, so this would be the force that holds a liquid together. If you break it apart, it can turn into a gas. So therefore, our boiling points will increase in the same direction, right? As the forces are stronger holding them together, you're gonna have to get to a higher temperature for them to change from a liquid to a gas. So what this does is, this affects their physical state. And by that I mean solid, liquid, or gas at room temperature. Okay, so that's just an overview, introduction to what organic chemistry is, homologous series, along with, what a hydrocarbon is, the 4 different groups, and kind of a little bit more about carbon itself.